of that. So once again, I want to welcome all of you here to the Valley of the Shadows of Research Method. It's been a pleasure having all of you. Now, in your exams, you will have a preamble about a data set. You are not going to run the data set. I have run the data set, and I'll rather be showing you some results, several results. In fact, I'll have about 8 tables and about 5 graphs that I will show you. And based on that, I will ask you a series of questions. So I'm going to use a regression topic here so that we understand them. Remember, this story is all about the Brukutu gene data set. Okay, it's about gene betas, the quantity demanded of gene betas. And we did mention that the quantity demanded of gene betas depends on some variables. Now, in case you probably have forgotten those variables, I can just show you the data sets so that you know and you can refresh your memory. I'm just going back. We've looked at the sample regression. All of these correlation metrics, you got to know them. Okay. So I'm just going to take this one and rerun the data set for you. And so I would encourage you to do the same thing. Go and run the data set. Okay, run the data set. Okay, so I'm starting multiple regression and I want to run the data set, but I want to go back here. So I'm just going to create a cell there and just load the data set. Okay. So the data set, I will import pandas and then use the usual CSV file. The name of the data is gene. So I'll run this to show just the top part. Okay, let me show the first 4 observations of the data set. So it's going to show down here. Okay, so that's what you have. So this is a data set where quantity demanded is a function of a series of variables: price, complement price, the average income of the people, the location of the shop, the occupation of the people, and the religion of the people. Keep this in mind. Keep this in mind. Okay. Now, I have set a question like this where I will ask you something about the data set. When you have a data set like this, when you are told that the data is many, but what you have is just the top part of the data set, you should be able to answer question about the data set. You should be able to identify which ones are numerical, categorical, and why, and all of that. So you should be able to know that. Okay. Now, we have the data set now. We are ready to generate our regression. We'll use the stats model, okay, and we'll use this. Now, I've already indicated last time we met that R was there long time ago before Python came. So when you write this thing in an R style, it helps to be able to showcase the thing well. You don't have to convert these things into dummy variables. They are already dummy in the brain of R. If you're going directly Python, you have to convert everything and dummify each of the variables, 0, 1, 0, 1, 0, 1, just to make it proper dummy coded. But here, R is so sensible. Okay, so I needed to get a package that will integrate the R principle here. And that's what you have there. So I call the name of the database. I use the quantity demanded with a tilde sign as a function of price CM LOCOCC REL. Apply that and then ask for the result. And this is the result you get. So let's see the results. It's going to pop right now. You should be doing the same thing. There you go. So you get the top part of the data. Okay. It gives you the key. It tells you what kind of regression you are running, which is a multiple regression, OLS, ordinary least squares. The date you did that, okay, is there. The time you did that is there. The number of observations, the residuals. And then these are the independent variables. So in this case, there are generally 8 major independent variables. Of course, some of the dummies will have level, which will make it mean. You have the R square, you have the adjusted R square, the F statistic, the p-value of the F statistic. Okay, this means that you have 28 zeros before the 9. That's what I mean. You have 28 zeros before the 9. You have the log likelihood. We shall talk about all these. The Kaike information criterion, the Bayesian information criterion. You have all of that there. Okay. Then you'll be told whether the model you have estimated is robust or is not robust. This one is not robust because we're not taking care of a lot of things like the assumptions of regression, heteroscedasticity, autocorrelation, misspecification, and so many things. We've not done that. We've not taken even the log of the variables. Then the major thing, you have the coefficient, the standard errors. Now, I want you to know something before we start properly. Oops. I don't know. Okay. So you have the coefficient. The coefficient, you should know that the coefficient divided by the standard error will always give you the t statistic. Keep that in mind. The coefficient divided by the standard error should give you the t statistic column. So this column 1 divided by column 2 will give you column 3. If you like, check it for every one of them. You see that. And then when you go and read the t statistic column or the t value column on the t table or the normal distribution table, you will get the p-value. The p-value is a p greater than the absolute value of the t statistic. That is a p-value. That is an alpha. That is the level of the measure of the significance. That will tell you whether the variable is significant or is insignificant. And then the latter ones are the confidence intervals of this p-value. So the confidence interval is a confidence interval for the coefficient. Okay. If the coefficient falls within the upper and the lower confidence interval, it shows that that variable is significant. Okay. So for example, if you take this one here, okay, which is a coefficient for so this is a clear indication that it's not significant. Okay. If you take the absolute value, is it? No, you don't even take the absolute value. Yeah, this is some of them might be explanatory well, some of them might not. But we'll come back to this. So that's it. Now, the most important thing I'm interested in are these. It gives you the location, and then it tells you whether it is urban or rural. It tells you the levels. So you get the actual thing together with the levels. And that is a key. That's an important thing that I wanted to know. Of course, the numerical variables are down here. Price, complement price, and then income. So let's go to our first question. The other statistics that you check here, for example, the Debin-Waston, the omnibus, all of these are measures of autocorrelation, measures of normality, measures of linearity, measures of outliers, and things like that. Okay. They are normally useful for residual diagnostic analysis. Okay, so let's go to the first question you will get in any model. And this is a question down here. Specify the entire regression model. Specify the entire regression model based on your result. So if you have a question like this, you got to go look at the result before you can specify the regression model. And watch the words. Using the same labels as produced by Python. So the name that Python gave is exactly what you're going to do. Now, what is a specified regression model? We said it. A specified regression model is made up of the dependent variable and the independent variable. Dependent variable is on the left side, the independent are on the right side. The independent variables are variables together with their beta parameters. They are not numbers. They are not numbers. A specified regression model has no numbers. They are all represented by betas. So you have beta naught, beta 1, beta 2, beta 3. And then you also have the error term. So how will you specify the regression model? What you do is you first go up here and then go and identify the quantity demanded. So when you come here, you see that the dependent variable is the quantity demanded. So that will be on the left-hand side. Okay. So you have that on the left-hand side, something like this. Then you do equal to, you write your beta naught. Now you will not get these answers I'm telling you in the table. You won't. But you got to have knowledge to be able to do that. So you have beta naught plus beta 1. Then you go and look down to look for the first independent variables. Just check the name. You can pick it as it is. Okay. So that is log urban. You write it exactly. In fact, you might want to write those that are not dummies first, which is PCM, just as it is. So you come here and you write beta 1 P. Okay. So let's add a P. Then you do plus beta 2. Second one was C, so you write C. Plus beta 3. The third one was M, so you write M. Plus beta 4. The fourth one is the one here, which is log urban. And this is where if you don't take it, you will just write whatever you like. But the rule says you should write exactly as it is. So you write log, okay, bracket T dot urban, just as it is. Just as it is. And that's it. Then you go to beta 5. And then go on and on and on till you get to the last one, which is plus the error term. Now, sometimes you can see the epsilon here being used. Sometimes you can see mu being used. Sometimes you can say, look, anything you decide to use for the idiosyncratic error is fine for me. So this is how you specify the model. So with that in mind, let me show you down here how this particular model has been specified. Okay. So this is a specification of the model. You can see clearly that I have specified and the quantity demanded is here. Ideally, it should have been Q. Then you have the price CM, and then I've also attached the I's to them. Now, in your case, for example, exam case, I will not expect you to write the I for each one. If you can do it, great. But you'll not be penalized if you don't write that. It just makes it beautiful. This is pure cross-sectional data set we are dealing with, so there's no problem. So I expect there's 5 marks for this. And then finally, you have the error term at the end. If you write everything and you forget this error term, everything is zero. Take note. If you write everything and you forget just the error term, is zero. So it's very important you know exactly what you are doing. Okay. The next question is this. Okay. Look at the next question. It says that write the estimated regression equation correct to 2 decimal places. So first was a specified model. Now you are writing the estimated equation. What is that? The estimated equation simply means go back to this original one here and change every beta parameter to a number. Change it to a number. How do you get the numbers? Go up there. The numbers are the coefficient column. So the beta naught is the intercept. So you pick this number, but remember it's correct to 2 decimal places. You take the next one, okay? You correct it to 2 decimal places. 2 decimal places for this will be what? Location urban. What will be the 2 decimal place for it? Negative 5.11. Okay, so you do the same thing for the rest, and finally, you're able to get this very final work. So this is your final estimated regression equation. It's very important you do this well because you use this thing for prediction later. So if it is wrong, your prediction question, which is 13 marks, will be wrong. Okay. So these are top top questions that I've asked you here. The next one is to determine the partial significance. Okay. Now, what do we mean by? Well, if you look at the above equation, okay, each one of these independent variables, price, complement price, they are all trying to influence the dependent variable. The dependent variable there is quantity demanded of gem bitters. Every one of these on the right-hand side is trying to influence. The question is by how much? By how much? And even if they are influenced, is it significant? So the essence of partial significance is to look at the individual importance, the individual role each of the independent variables is giving to the dependent variable. Okay. What is your role? We are all trying to affect the dependent variable quantity. What is your role? So let's look at that. Now, to identify the partial significance, you got to go here. And I've indicated it. So most of the time, because it's a test statistic, the null says that the independent variable or the feature is insignificant. And the alternative will always say that it's significant. You can use the confidence interval as well to tell whether it's significant or not. Okay. But most of the time, you're going to use the p-value. So the proper question here is, which regression estimate, see another word I've used for independent variable, which of the coefficients, that's another way of saying the estimate, which of the coefficients are significant? Justify each one. Okay. In other words, do a partial significant test. I've changed this question slightly. So let's go to the model. Which independent variable is significant? Now, to tell whether an independent variable is significant, check the p-value. If the p-value of the independent variable is more than 0.05, or if it is 0.05 or more, if it is 0.05 or more, then it is what? It is insignificant. It's not significant. But if it is more than, if it is 0.05 or more, it's not significant. If it is 0.05 or less, it is significant. So let me put it this way. If it is more than 0.05, more than 5%, it is insignificant. If it is 5% or less, it's significant. So you can look at each one of them and tell whether it's significant. The intercept is not part. So I want each one of you to look at each one. Okay. Just be prepared. I'm going to mention your name. I'll try the first one for you. Okay. If you check location urban, now check the p-value for location urban. It is 18%, approximately 18.7%. And that is way more than the acceptable limit of 5%. So my question is location significant in determining the quantity demanded? And you have to give a reason. Is it significant? Just be ready. David Oku. Is location significant, David? David, you can go ahead.
Hello.
I can't hear you.
Hello.
Go ahead. Go ahead.
Yes, it's significant.
Why?
Because the p-value is more than the, like you said, it's more than the usual accepted 5%.
You are guessing because you are wrong. You are wrong. And that was why you delayed. You are wrong. Let's go to another person. Jibody.
Sir, please kindly repeat the question again.
Why you weren't paying attention?
Sorry, please. I stepped out shortly.
If your video is on, you wouldn't have stepped out. Which independent variable is significant and which are not? So we are starting with the location urban. Is it significant or insignificant?
Says 0.0. It's insignificant.
Why?
Because it's greater than 0.05.
What is?
The P
What is
value.
it?
0.187.
And that is how many percent?
That's 1.87%.
No. How many percent is that? Wow. You don't know how many percent it is. Forgive.
Yes, Doc. So the location is not significant because it is greater than the p-value, which is 0.05 at 5% confidence interval. So at 5%.
What is your conclusion?
So location is not play a significant role as a variable to the output. Therefore, we can reject in terms of.
All right, your place is very noisy, and I think you know that already. You have not positioned yourself well for today's lecture. All right. Let me go to Isaac Ousajuman. Isaac Ajeus. Isaac, what would you say about occupation teaching? Is it significant or insignificant?
Look, occupation teaching is significant because it is lower than the p-value of 0.05.
It is lower. What is that? That's lower.
Okay, so the p-value is 0.000. That's 0%, which is much, much lower or very good, very excellent as compared to the limit of p-value of 5%, 0.05.
Good. Excellent. You're thinking like that. Let me go to the next person, and that is Victoria Emenike. Victoria.
Yes.
Go ahead. Religion Muslim.
Religion also, it's also very significant because it's very percent, which is lower than the limit down to significant, which is 5%, therefore very fine.
Okay. Good. Theophilus crunching. Price. The one I've highlighted. What would you say, Theophilus? Theophilus crunching.
Hello, sir.
Go ahead.
It is insignificant because the p-value of 0.053 is greater than the accepted of 0.05.
Very good. In principle, watch this, guys. In principle, it is significant at 10%, but it's not significant at 5%. Write it down, because I've set a question related to that. You see, when the p-value is more than 5%, it's insignificant. In this case, it's a little more than 5%, so it's insignificant. Okay. However, there are three major significant levels you can use. You can use 1%. Actually, there are four. You can use 0.1%. Then you can use 1%. Then you can use 5%, which is a default. And then you can use 10%. So the p-value will tell you that a variable is not significant at the default 5%, but it's significant at the 10%. We don't have 20%, we don't have 15%. So this variable of price is not significant given the 5% level, but it's significant at the 10% level. Rancho, do you understand?
Yes, Doc.
All right, okay. All right, let's move on to the next one. The next thing in our exercise is this question about, so all the significant, I've left it as a gap for you to fill in. I said which regression estimates are significant, okay? So you have to go through each one of them and then indicate why it is significant, why it's not significant, why it is significant, why it's not significant. You have to do that. You will face a similar one in your assignment, in your exams. So it's important that you know how to execute it. Okay. The next one is the joint significance. The joint significance. Okay. Okay, so here I've just moved to rather the interpretation. We'll come to the joint significance very soon. So how will you interpret the independent variables? Now remember, some of these features are numerical, some are categorical. So here I've given you the option to interpret one categorical, one numerical. The numerical is price. The categorical is religion Muslim. Guys, I'm going to say it, you should type it. You should type it because there are some keywords you are supposed to have when you are interpreting. You miss those keywords, they are going to be dangerous. I'm going to say it because I've learned this thing for years and it's stuck in my brain. So I'm going to interpret the coefficient of price, which is negative 3.15. There's a reason why you bring the negative. Okay. So let's start with the static variable price. How will you start and interpret it? On average, that's what you write. Okay. On average, because, okay, on average, given the complement price of gin, the location of the people, sorry, the location of the shop, because this one is the shops of gin bitters. So let me start. On average, given the complement price of gin, the location of the shop, the occupation and religion of the people, a 1 unit increase in the price of gin decreases quantity demanded of gin. The 1 unit increase in the price of gin decreases the quantity demanded of gin by 3.15 units. By 3.15 units. If you are stuck at any point, you didn't hear something, let me know, because this is not exactly in your slides. So it's very important you are learning how it works. On average, I'm repeating it. Given the complement price of gin, income of the people, location of the shop, occupation and religion of the people, a 1 unit increase in the price of gin reduces the quantity demanded of gin by 3.15 units. By 3.15 units. All right. I repeated it because Victoria said I should repeat. So look at the words. First of all, the average will be marked. Now, because we are interpreting the price of gin, if you check it, when we're holding the other factors constant, and by the way, never say that holding all other factors constant. When we're going to make the other variables given, we didn't do that for the price of gin. Check it. It was for every other variable except that of the price of gin. And when I say every other variable, you can see the every other variables, they are all here. So when you look at all of these variables, the major one that we're going to interpret was the price of gin. So we spoke about every other variable except the price of gin itself. Also, we indicated that when we got to the occupation and religion, I didn't say occupation of the people and religion of the people. I combined it. It's a good English style, right? Then because price is rising or falling, it's not static, I indicated that a 1 unit rise in the price of gin. So the 3.15 is not for price. It is how the Q is going to change, how the Q is going to, in this case, fall in case price should rise by 1 unit. Remember, I said unit. I did not say percentage. I didn't say 100% increase in the price of gin. I did not say dollar, $1 increase. No, I said unit. The unit of measurement can be anything. If you know the exact unit of measurement of these facilities or products, you can actually incorporate that. Other than that, you keep it as units. That's how you interpret the coefficient of price, which is static. Now, the fact that you are increasing it, which is leading to a decrease in the quantity, that alone shows that it is what? It is a dynamic variable. It's not static, it's a dynamic variable. It's changing, it's rising and falling variable. It's not clear. We are going to interpret that of Muslim, religion Muslim, and you see that the way you interpret it, a dummy variable. Religion Muslim, a dummy variable is a variable that is not changing. So religion Muslim is not changing. It's static. You are either a Muslim or you're not a Muslim. It's not like every year you are changing your religion. So we are going to do, but because it's a dummy, you need to compare it with a reference category. Now, if you check carefully and you look at the results, and you look at the results for religion, all the results for the religion, there were 3 actually, but this result omitted 1. So that one that is omitted is called a reference category. Write it down. Write it down. The one that is omitted is the reference category. Every time you're talking about this religion, you got to speak as though the reference category is here. But you can see in the results that a reference category, oh, by the way, which other religion is not here?
Buddhist.
Good. So you got to speak in relation to Buddhists. So I'm going to interpret the coefficient of Muslim, but I'm going to speak in relation to Buddhists. So write this down. On average, and because I'm going to talk about Muslim, I will hold everything about religion constant. Well, they are already constant in this case because they are static. So on average, given the price and complement price of gin, the income of the people, given the price and complement price of gin, the income of the people, given the price and complement price of gin, the income of the people, the location of the shop, and the occupation of the people. So I didn't bring anything about religion because I'm interpreting religion. And the occupation of the people, quantity demanded is predicted to be, that's how you say it. Quantity demanded is predicted to be or expected to be. Quantity demanded is predicted to be or expected to be. Of course, you can choose one. It's predicted to be 23.01 units. I'm picking it from here. 23.01 units less. 23.01 units less. If the people are Muslims than Buddhists. If the people are Muslims than Buddhists. Quantity demanded is predicted to be 23.01 units less if the people are Muslims than Buddhists. Okay, why did I say Buddhist? Because Buddhist is a reference category. So before you interpret any dummy variable, you got to know the reference category before you even start the interpretation. There is 4 marks for each interpretation. So take it serious. And you'll get 2 like this out of the whole to do. Of course, you're not going to use this data set. Let's go to the next thing. The next thing is about how the model is good. How good is your model? How reliable is the model? We call it the fitness of the model. Is a regression model well fitted? Is a regression model reliable? The fitness of the model. So the question is a regression model well fitted or is it reliable? And whatever results you use to interpret your results using these 3 things: R-squared, log likelihood, and then the Bayesian information criterion. Now, guys, there's some bit of information about each one of this, but I want you to know some key things. One, the R-squared is called a coefficient of determination. The R-squared is that portion of the variability in the dependent variable. That portion that has been explained by all the independent variables. Remember that each independent variable is trying to explain a certain percentage of the behavior of the dependent variable. Every feature is trying to explain or influence the behavior of the target variable. How much together, how much in all of them are contributing to this influence? If they are contributing 100% to the influence, it means they are all relevant. So the R-square will tell you whether the independent variables are doing a good job in explaining the behavior of the dependent variable. And that is measured by the R-square, the coefficient of determination. Now, sometimes the R-square is supposed to reduce, because for example, if I tell you that you should include variables, and now you begin to include irrelevant variables in the model, So let's say we are talking about the factors that determine the quantity demanded of gym bitters. Then all of a sudden, somebody goes to write broken heart. Then when you actually have broken heart, you now go and take a lot of alcoholic beverage. That's why. That's one thing. Now, this is an irrelevant variable. But suppose you force to include it in the model, the R square is supposed to come down because it's not relevant. Unfortunately, the R square is not designed to come down. So we need something called adjusted R square, which is also called R square bar. The adjusted R square, which you see here, okay, the R square bar, what it does is that the more you are including target features, predictors, regressors, independent variables, and they are relevant, that's okay. But if they are not relevant, the adjusted R square will come down. So in principle, the adjusted R square is always lower than the R square because it will punish irrelevant variables. Now, let me ask you a deep question. If the R square is equal to the adjusted R square, what does that mean? What does that mean? If the R square then is the same as the adjusted R square. Rashid, are you here? What does that mean? If the R square is the same as adjusted.
It means that the model is significant.
Hmm?
It means that the model is a good one.
No. It's the same thing she has said. I only want you to repeat what she said and add more.
Okay, so my understanding is that we get adjusted R squared by reducing the number of independent variables. So if
No, we don't get adjusted R squared by reducing the number of independent variables.
Oh, okay.
When you reduce the independent variables, the R squared can still be equal to the adjusted.
So that's why, like, I wanted to use that one to explain. I don't know, but you said it's not like that.
The R squared. The R squared is there to penalize rather the inclusion.
Okay.
Is there to penalize the inclusion, but not of independent variables, of irrelevant independent variables.
Okay.
Not just any independent variable, the irrelevant ones.
Okay.
So if you include an independent variable that is relevant, no problem. R square and you have no problem. All right. Okay, so let's go to my question now. Is a regression model fit? To determine the fitness of the regression model, you always use the R square. I have given a rule. Even though there's no clear-cut rule, I have given you a rule based on hair black it up. That whenever the R square is bigger than 50%, then the regression model is well fit. Full stop. So regression model is reliable when the R square is more than 50%. That is just an approximation. But I've also made a point that a good model can have a very low R square. So a model can still be good, but the model, I mean, I'm talking now about practical sense, not for exam purpose. For exam purpose, yeah, when it's bigger than 50% is good. Now, you can have a very good model, but the R square is small. I have seen a model where the R square is 11%, 5%, especially in social sciences, and it is acceptable, provided that most of the explanatory variables are significant. Okay, because if the explanatory variables are significant, you can't say that, oh, we should remove them because they are irrelevant. They are significant. So an R square of 41% is neither good nor bad. It simply means that we are missing some information. A good one, a good information. Okay. So the best thing when you're in practical world, the best is for an R square would depend on a particular situation. And you have to look at the situation before you conclude. All right. How do you interpret our R square of 99%? It simply means that 99% of the variability in the quantity demanded of gene betas has been fully explained by all the independent variables. It simply means that we've explained 99% of the variance in the data set, especially compared with another without any independent variable. The question said you should also use a log likelihood model statistic and then the BIC. Now, the log likelihood is given by this formula. Okay. It has, the good thing about the log likelihood, you should notice that it tells you how likely the observed data is under the model. It is always negative. Let's go and check yours. So if you look up here, the log likelihood is above, and it is what? Is negative 102.94. To be honest, the log likelihood is normally used for when you're comparing models. So let's say that you remove an independent variable, then you calculate it. Then you see that, oh, one independent variable has got this log likelihood. Another has got this different likelihood. Which one should you go for? Okay, the model that is a fit model, is the one. So if you have a particular model that has a log likelihood model, if you have a log likelihood model that is more negative and bigger than the one we have, then that model is better. So in terms of absolute value, the bigger the log likelihood value, the better. Like I said, it has to be compared with another variable. And then the Bayesian information criterion is given by this. It has two things: penalty for complexity and then the fitness of the model. Okay. But the key point about this is this. It's the same thing as the R square. If you have a value that is bigger is said to be better. Okay. So you want a bigger Bayesian information criterion. You can read a bit about this. Now let's go to the joint significance. The joint significance will always be you answering this question. Okay, determine the joint significance of the model. Class rep, if you are here, tell all those that are left to rejoin. Based on the p-value, I'm going to take a screenshot. You always check the p-value for the F statistic. And if the p-value is less than 5%, then the independent variables are jointly significant. One of the things you should notice that the R squared doesn't tell you whether the model is significant. It only tells you the percentage. But the F test tells you whether the model is significant. So an R squared can be low, and yet the F test will still tell you that it's significant. All you got to do is to check the p-value. In our case, the p-value, if you check it above, it was 0. It was 0. And because it's 0, it is less than 5%, and therefore, all the coefficients are jointly significant. The next thing is to use the model for prediction. Okay, use the model for a whole lot of prediction. I've given you the prediction situation here. I will encourage you to read all that you got to read when it comes to prediction. I have done one of the prediction for you. I gave you a scenario. So if you look at this part of the model here, this is estimated regression equation, the one with the coefficient. This is it. Okay. Suppose we know the values of each independent variable. We know their values. Then when we substitute those values, we can predict the quantity demanded. In this case, the beta parameter, which was irrelevant, can now be relevant. I mentioned in the early part of this course that the beta parameter, the constant, the intercept is for beautification. It has no real economic interpretation unless during prediction. So once you know the values, you can substitute the values and you can find the value of the dependent variable. So in this example, you were told to compare the predicted quantity of gym bitters by some Muslim traders in an urban town. Watch the word, Muslim traders in an urban town. Compare that with the quantity demanded produced rather by Buddhist fishes in a rural area. So you have Muslim traders in an urban area, Buddhist fishes in a rural area. In both cases, the numerical variables are the same. Okay. For example, the price of gin is 15. The complement price of gin is also 15. And the average income of the people is 20. So in all cases, you have that. But then the differences are coming from those things. For example, religion. One is Muslim, the other is Buddhist. Also from location. One is urban, one is rural. And also from occupation. One is traders. One is traders, and the other is what? Fishers. So what do you do? Well, the first thing you got to do is to substitute for the first scenario. Okay. So watch it, because the dummies, so if you look at the dummies for teaching like this, let's start with urban. The first scenario says that they are Muslim traders. So if they are Muslim traders, and then it says they are in an urban area. So urban area means when you get to here, the value should be 1 because they are urban and it matches with this. Okay. Now let's go to occupation. Occupation, it says that the people are Muslim traders. So if they are Muslim traders, when you come here, which is not traders but teachers, the value should be 0. That is why you can see that when you come here, the value is 0 for teachers. They are Muslim traders. They are Muslim traders. So it means that when you come to trading, the value is what? 1. So again, when you go here, you notice that the value is 1. We are also told they are Muslims, which means the religion is Muslim. So wherever you see Christian for this first scenario, because the people are Muslim, Christian here will be 0, which means they are not Christians. And then Muslim here will be 1 because they are Muslims. Learn how to substitute this, because the substitution alone is 3 marks. Before the calculation to get another 7 marks. That's 10 marks in this case. That's how you execute this variable. You do the same thing for the next one, and then you compare which one will give you a bigger quantity demanded. So I've done the first one for you, but I've left the second one for you. Based on that, you should be able to conclude. Look at the question. Okay, towards the end, it says that what factors are driving the difference? The factors are the location, because the location was different between the 2 scenarios. The factors are occupation, because occupation was different between the 2 scenarios. And then you can find that of the rest. Remember that price was the same. Complement price is the same. You will get a different situation in your work. Now, one last thing before we wrap up is multicollinearity. That's the last thing. By the way, you can look at other things. This will come in your practical work, your thesis, where you're looking at prediction accuracy. How accurate are the predictions by using all of these prediction accuracies? So I've given them to you. You might not see the usefulness of them yet, but they are really powerful in your practice. Okay, let's go to the last one for today, because I'm scratching the surface of regression for you, not the detail. It's multicollinearity. One of the assumptions of regression is that the independent variables should not be multicollinear, meaning they should not be highly correlated with each other. If 2 independent variables have got a correlation coefficient of 0.9, which means that they are almost perfect, 100%, then it means that the 2 are doing the same thing. And so you don't need to keep both even in the model, because it becomes redundant. Okay, it becomes redundant. So multicollinearity is where 2 independent variables are so highly correlated that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. That's multicollinearity. It can be a case. Okay, a typical example of multicollinearity is weight and height. As a person's height is increasing, you will see that the weight is also increasing. The 2 might be highly correlated, too high, to the extent that they become multicollinear. Another is experience. I gave you an example of that the last time. And a perfect example is male and female. See, male and female, if you are not male, you are female. So that is a perfect opposite correlation. Because 1 minus male is female. 1 minus, female is male. That's perfect. That is why, and keep this note, that is why we don't normally do the correlation coefficient for dummy variables. Because dummy variables are dummy. They are 0 or 1. They are categorical. And if they are categorical, they are likely to have, 1 minus the other. So if you have occupation to be trading, and then you have another occupation to be fishing, and then another occupation to be teaching, 1 minus the teaching is going to be either the two. So because of that, we don't do multicollinear analysis or correlation analysis for dummy variables. Keep that in mind. Okay. So an R-square can be high, but we can check the standard errors, and then we can see that the standard errors are still very, very bad. So you can have a higher R-square. I've said this multiple times. A lower R-square doesn't mean that the model is bad. A higher R-square doesn't mean the model is good. So let's go to how to look at multicollinearity. How do you check whether it's there? How do you check? Is it there in the model? Well, to do that, you use something called variance inflation factor, the VIF. The variance inflation factor is just 1 divided by 1 minus the R squared. Sometimes you can choose rather to use the tolerance level. The tolerance level is just 1 divided by the variance inflation factor. That is how much you are willing to tolerate a particular independent variable. What is the rule? Well, there's a certain rule of thumb that if the VIF is 1, it means that there is no correlation between the independent variable. Okay. You see, remember, we are looking at the VIF of one variable and another variable. So you check the VIF of that. It means that variable is not causing a problem. But if you check the VIF of some of the independent variables, and then their VIF are higher than 10, that means that there is some serious multiple there. There's some serious multiple there. Now, let me ask you a question, and this can go to anyone. What do you think is the VIF value in a simple regression? What do you think? In a simple regression, we have one dependent variable and one independent variable. What do you think is the VIF value in a simple regression? Let me see if I can pick on someone. Ernestation, Joseph Ernest. Joseph Ernest.
Doc.
What is a VIF value for simple regression?
Doc, please, it's 1.
Why?
Hello?
Why? Why is it 1?
Because there's no correlation with other independent variables. There's just one independent variable and then there's a dependent variable.
Good. Good. Go and find out. Go and find out arrangements. Okay. So that is the VIF. So let's go to our variable and check which ones might be highly correlated. This command, which I've given you, will generate the VIF value. So it has generated the entire regression again. Okay. And look here, it has also generated everything here. But at the bottom, it's generated the VIF. And even in this one, it has added the VIF at the last column to the other independent variable. It's so sweet. Now, even though it has produced the VIF of the other independent variables, check carefully, even though it has produced the VIF, you should note that the dummy variables, their checking of VIF is not going to be necessary. You're not going to use it because we've already said that dummy variables, the VIF will surely be, like we don't need to look at their VIF because you cannot check a correlation with a dummy variable. It's not changing. That variable is not changing. So I've written here that you focus on the price, the complement price, and then the income, this one. So looking at price and complement price and income, look at the last three here, the numerical variables. Look at their VIF. Remember, the most dangerous VIF is when it is bigger than 10. Okay. And when you look at it, all of these variables are bigger than 10. So it means they are a problem. How do you handle it? Normally, the best to do is to remove each one of them one by one and rerun the model. So first you remove the price, run the model again, and see the VIF. Or see the coefficient of the results. Then you now bring the P back and then run and remove the M. And then you bring the M back and then you run and then, do for the C. That is how so you see which one is the problem causer. But you can't remove all of them at a go because you have to know whether this one, its presence or absence make a difference. That is how you attack this. Okay, so now I'm going to give you some areas of your exams.